perhaps one of the biggest influence finance has had on the operation of financial markets was the discovery of a mathematical model that accurately prices options. These models appeared in 1973, and the primary model that we talk about today is the so-called Black-Scholes option pricing model. This model was pioneered by Fisher Black and Myron Scholes and published in the Journal of Political Economy in 1973. The same year, Robert Merton published the Theory of Rational Option Pricing. These two articles together provided the foundation for option pricing. Now, I'm not going to go through all of the details of the Black and Scholes option pricing model, but I do want to give you the basic underlying intuition of what's going on in the model. And the first thing you should notice is that it is remarkably simple to price an option when there's no time to expiration. So a fraction of time before expiration, if we've got a call option and it gives us the right to purchase 100 shares of IBM at $200, and if the price of IBM is $215, then the option must be worth $15. So the whole contract would be worth $1,500. It makes sense because we're just a fraction before expiration. And at expiration, I know that I can purchase the share for $200 and sell it immediately for $215. So the price of the option at expiration is the underlying stock price, and we call that S. And at expiration, I often mathematically denote it as S star, minus the exercise price, which is K in the mathematical notation. So in this case, it's $215, which is S, minus K, which is 200. And that is the price of the call option. Now, this example is trivial. You don't need a mathematical model to figure it out. At expiration, if you get to buy at 200 and you can sell at 215, the option must be worth 15. The real question is, what about before expiration? And this is where the model of Black and Scholes and Merton comes in. Now, it's real clear what will make the option pay off. The option will pay off if the underlying asset achieves a final value above the exercise price. So how can we actually put this into a pricing formula? And if you stare at the Black and Scholes pricing formula, you're going to see some similarities to the value of the call option at expiration. At expiration, we know the formula is simply S star minus K, our example that was $15, or 0. You take the maximum of the two. If it's the case that the stock price finishes at $190, the call option finishes out of the money. In that case, S star minus K is a negative number, and we would take the maximum, which would be 0. Now, if you look at the Black-Scholes formula, without actually going into the details of the formula, you'll see something very similar to S star minus K. Except we don't have S star in it. We've got S, the current stock price, in it. And we don't have K in it. We've got the present value of the exercise or strike price in it. And it's more complicated than this, in that we need to mathematically determine what the probability is that the call option finishes in the money. In other words, what is the probability that the underlying commodity price exceeds the exercise price by the time of maturity? Now, the idea that Black-Scholes had was that they made certain assumptions about how the stock price would behave. So they made the assumption of stock returns following a certain type of process. And for us, we can think of this in terms of the normal distribution. So you could think of the returns with a normal distribution, and there's a certain mean return that you expect, and there's a volatility. With that information, given what we expect in terms of the mean or the average return and the volatility, we can actually calculate what the probability is that the stock price finishes above a certain cutoff point. And we can calculate that in a fairly simple way using the cumulative normal distribution. And these are the inputs for the Black-Scholes formula. So using, in particular, the volatility of the underlying asset, we can calculate the probability that the underlying stock price finishes in the money. And this is the essential ingredient for the Black-Scholes formula. Now, I've highly simplified what is actually going on. But when you look at the actual formula, you can see the essential things are there. The essential things being the stock price minus the present value of the exercise price. It makes sense it's present value because we're not at expiration, we're today. And everything needs to be adjusted to today's values. You're going to see the cumulative normal distribution, which gives us a sense of how likely the stock price will be to exceeding the exercise price. You're going to see within the cumulative normal distribution the volatility of the underlying commodity return, which is essential. You're going to see the time to expiration within that formula also. All of these things that we've talked about in terms of the determinants of the option value appear in the Black-Scholes formula. However, the essential intuition is quite straightforward. We know that the option has value if there's a probability that the underlying commodity value will be above the exercise price. And this is basically the foundation of the Black-Scholes formula. The Black-Scholes actually provides a mechanism. It makes assumptions on the so-called stochastic process of the underlying returns in order to deliver a model that gives the price of a call option.